We have the first presentation. It's Designing and Achieving a 100-Year Service Life. Our presenters are Siva Venugopalan. He's president of SCS Incorporated. And also, this is a co-presentation. Will Pines, who you met earlier, he's the executive director of Maryland Transportation Authority.
Well, thank you, Rod. And more important than my state service, Rod didn't mention he was my former boss. So, yeah. Well, thank you. How many bridge owners do we have in the room? Few. All right. So the portion of the presentation I'm covering is really kind of tailored more towards speaking to bridge owners, but Siva will cover a lot of the topics that hopefully will interest industry as well, but I think everybody will have some good takeaways from this. So why is service life design a big deal? What are we talking about here? So I think everybody recognizes that major rehabilitation and preservation projects that really oftentimes come with major impacts to the public and costs in terms of user costs. And ultimately, all of us should be focused on bridge safety. You know, that we hear in the news when major incidents happen, what kind of negative reputational issues come with it. And so designs that are focused on extending service life help us to provide better conditions for longer, which ultimately gives us a greater degree of confidence in the safety of the assets. And so one of the things that we'll talk about in this presentation is what do you actually get when you design a bridge by quote-unquote code? Some folks may not realize what service life means in terms of their design. But we do think that given the amount of effort that often goes into designing what I'll refer to as monumental bridges. Oftentimes they require monumental support, and that's from elected officials and financing. And so service life is a really important thing when you're talking about those really exceptional projects. So how long is long enough? A lot of times our presentation title initially was really focused on a 100-year service life. That's kind of a buzz term today. But the AASHTO LRFD code that most of us use, that has a 75-year design life. And when you say there's different terminology here, you got design life and service life. Design life is really the amount of time that your code used to say the loading that you're using for this design will still apply. It's not really a measure of durability. In terms of durability, that's where you kind of get into service life, and there's not really a prescribed service life. Service life comes in different measurements. You can have a technical service life, which sort of is when do you reach a point where your service is unacceptable. That could be cracking or delamination, whatever safety kind of issue you have. You can have a functional service life where the traffic is too bad on the structure and it needs to be replaced because you can't live with that daily. And then an economical service life. Do you have to make so many costly repairs and investments in a structure that it would really just be cheaper to replace it? So service life design has a lot of different measures that are important to consider as you're doing it. And I would say many folks, unless you put intentional thought into it, you probably don't actually know what your actual service life is. What did we used to get? Anybody who designed with the AASHTO standard specifications may not realize it, but the design life, what the loads were designed for, was only 50 years. And the service life was really designed primarily around things like crack control, in clear cover, those types of deemed to satisfy criteria in the code. So there was no specific service life requirement specified for bridge structures directly in the design. So Federal Highway has indicated that more than 30% of the bridges in the country have exceeded their theoretical design life, that 50-year measure. In terms of Maryland, I did at one point in the presentation had a slide for the nation, but found that the data was very similar to Maryland. Ultimately, most of the bridges around the country were built when the Federal Aid Highway Act passed, and that was 66 years ago. And so many bridges have already exceeded that theoretical 50-year mark. And you look at the age of bridge structures, most bridges do not make it to 100 years. Most are 60 years or less. I noted that in my last slide, the average bridge age was 54 in Maryland, but you can also do certain treatments, and this aligns with deck replacements. We see from the NBIS, National Academy of Science, published some deterioration models on what should you typically expect in terms of decks. And you also see that 50-year number is pretty common, that bridges will often have deck replacements in that 40 to 60-year time frame. And so that's most likely driven by just using a standard design. Many bridge owners operate in that worst first kind of mentality, where you focus on addressing your most critical condition-based needs. That sort of drives you to doing these large major rehabilitation projects. But I think we all know, and we heard it from some of the earlier presentations today, that if you make incremental investments over time, that's one strategy to extend the life of structures. But you can see there is an option where you could just do no preservation on a bridge, and that tends to have the lowest service life. You have just a straight decline from good to fair to poor condition. But is there a way, using some intelligent upfront design, to shift that curve where you could do less preservation but make some initial investments that allow for a longer service life without needing that major condition-based investment down the road? So there's, if you look at some of the design guides that are out there, there's really two major strategies on how to achieve a service life design. One strategy is called, is really based on trying to avoid deterioration and set up to where you have either a deemed to satisfy criteria. That's where you have minimum covers and criteria in your design that allows you to avoid certain conditions. This is a more tailored design for your specific conditions, and it can be probabilistic or at least partially probabilistic. Then strategy 2 is where you start to make heavier investments, but they give a greater level of assurance that you've avoided vulnerabilities. So, for example, you can just pay the upfront money and put in stainless steel reinforcing, and most of the studies will show that stainless steel reinforcing is inert enough that it typically will last longer than 100 years. But it costs more. So do you want to do that everywhere, right? Likewise, you can invest more in joint details that are more costly, but that help to completely separate your bearing lines and your superstructure from drainage areas that helps you essentially avoid that vulnerability entirely. In terms of where are we in the industry, what guides are out there, how can we actually know? We talked about the code doesn't inherently tell you what your design life is, but there are tools out there. There's a guide that was published in 2020 that really does focus on service life design. It has this good, better, best approach, which really relates to, as a bridge owner, what level of rigor do you want to put into the analysis? Do you want to make a lot of investment in having engineers really design specifically for your conditions? Or do you want to get closer to that avoiding strategy where you're just going to pay a little bit more money in the construction and have greater assurances with the materials? So I'm going to talk about the MDTA approach within Maryland. Rod works for our sister agency, Maryland State Highway Administration in Maryland. I work for MDTA, we're the state's tolling agency. And we have two separate components of this presentation. One is focused on standard bridges, and this is sort of like, what are we gonna, I talked about how when you design by the code, you don't necessarily know what your service life is. What do we methodically get out of our standard bridge designs? And how do we do that in a way that minimizes our life cycle costs? So it allows for some condition-based maintenance, but maybe not others that are more costly. And then our approach that is more project specific on those monumental bridge projects where we're going to allow for some deviations from the standards because of the magnitude of the cost to do that project. Before I get ready to turn it over to Siva to kind of get into the details of how SCS helped us do that service life analysis for standards, I think it's just important to note that MDTA has historically used the M.SHA standards for materials and construction, and we've also used the structural details and design guides. That's kind of statewide. If you put out a project, you can do it quickly because a lot of our details are already prepared. We wanted to retain most of these. We didn't want to get into where every project was being designed specifically for the unique cases. We wanted to have some of those more avoiding strategies, but did not want to get into changing our clear covers, changing our materials across the board. And so we were really looking at what bridge deck reinforcing would assure us that 75-year design life while avoiding major condition-based life cycle actions that would really drive up the cost. And so it's the goal for us is within that 75-year period, achieving that life with the minimum life cycle costs. With that, I'll turn it over to Siva to talk about the analysis that they did.
It's really important. Each of the owners have different goals in terms of how they want to approach the structure, how they want to maintain the structure, how they want to extend the service life, and what's the overall cost involved, and how complex is that going to be? Is that going to be possible to be able to do it within their, the resources that they have? So one of the things that we were looking at in this particular case, owners, MDTA was asking the question, hey, Siva, we don't want to change our suppliers, and we don't want to change our mix, mix number 6 that we use for the deck. And we really would like to know, based on the conditions and the salt we put on, and assuming we're getting the same mix, what other element that we can change to extend the service life from here to there, and what's the life cycle cost for those different materials that we can use. Can you give us an idea? So what we did to do that, we needed to get some idea of what the total, salt that they put on the road. And we need to get an idea of what the surface is going to be, what the rebar level is going to be, so we can calculate the diffusion aspects of things, particularly from surface chloride that we would know. So we collected data from about 50 different bridges along that corridor, north-south corridor. And we then statistically analyzed those, and we were able to come up with the surface chloride loading over the last 25 years, what they've used, and used that parameter in our design modeling to be able to come up with, the different solutions we're looking at. Now, those are the blue dots that you talk about. Those are the bridge deck that we collected the samples from. And the green dots are the locations where we collected all the temperature, humidity, a number of different things that we need for our probabilistic modeling for the service life. So given that, once we collected the data, we collected chlorides at different depths, and then we fit that to a curve and then projected that to a surface chloride level. So we have a good idea of, overall, based on all of the chloride that they put on the roads, this is what the surface chloride is going to be with a min-max range that we used. And then we had different suppliers that they were using within Maryland for Mix 6. Mix 6 is primarily used for the deck, and Mix 3 is used for the substructure. So we kind of focused on Mix 6 because this is the deck. And so we collected samples from 4 different suppliers, like as though they would submit to a bridge deck work. And we then used that to calculate what kind of chloride migration those particular concrete types would have. And you can see, based on that CMC values, and we run that system through, you can see from supplier 1 through 4, the service life for a black bar varies quite a bit, anywhere from, 10 years to 23 years. And so even though they're giving the same Mix 6, depending on what gets into the structure, you could have significant variation. right? And then look at the cover, and normally the design cover is about 2.5 inches, and most of us use 2.5 inch cover. However, in the real world, the cover can vary anywhere from typically 2 to 3 is what we see. Sometimes you could be 1.5. And you see that service life significantly reduces, when the cover goes below the 2.5. If you can get a 2.5 inch cover, and this is not for black bar, by the way, this is for one of the alloyed steel that we were looking at. Even for alloyed steel, if you can see, if your cover is reduced, it only has a certain level of threshold, so the less of the cover, the chloride is going to get to the steel and the corrosion is going to go. So you want to keep that in mind. That all these combinations, you really have to work them to figure out where is my limit, what can I use, and what is needed absolutely. And the rebar type, there are different rebar types you have. A plain carbon steel, black bar we call them, epoxy coated, and the 1035s are the different alloy steels. And I just picked one alloy and put it in there. You got several varieties of those, different chromium content and corrosion resistant values. So there's a lot of them, including galvanized steel and all that. So then the stainless steel, which is in a totally different category all in itself. It's got significantly much bigger life, so to speak, than what we would ever design a structure for. However, sometimes you could have a situation, recently it happened, nickel was impossible to get. Stainless steel pretty much canceled all their contracts, so we couldn't get stainless steel for a while. So things like that can happen. So you're going to always look for what alternative do I have. And even though stainless steel has a lot of life, do you really need that life? Maybe in a marine environment for a substructure, maybe. Elsewhere, we may not need that. So just kind of keep that in mind. So what kind of life cycle cost are we looking at in terms of all these different steel we have? Each of them have a certain life and a certain cost associated with that. Comparing those, which one has the lowest cost? That's what Federal Highway drives, and that's what most of the owners want as well. What is the lowest life cycle cost? What's the second lowest life cycle? So we have a couple of different options for me to be able to do this. In this case, as you can see, alloyed steel has the lowest life cycle cost. And, you could look at epoxy coated being another option in terms of the cost perspective, and stainless steel is the highest cost, so to speak, from a standpoint. Why is that? If it's going to give you 500 years, why is the higher cost? Because you can't count that to 500 years. The design life is only 100. So you have to look at it from the aspect of, here's my design life, here's my service life, and what is going to control, right, overall. So you're going to look at that, calculate the cost of that. So you're going to keep that in mind. You can't build something unless it's going to be some kind of monument, right? And that's a different way of analyzing.
And so what was our outcome? In the end, we did update our notes and our general standards. The analysis found that the initial cost of stainless steel in a standard deck design was typically too high to offset the future maintenance costs. However, there are some opportunities with stainless, and we'll talk about it a little further in the presentation, that some of the higher strength stainless can allow for customized deck designs. But again, for this specific analysis, we really didn't want to go to that customization. We were focused on standard bridge decks. And so ultimately, we did elect to update our standards to incorporate the ASTM A1035 chromium content 9.2%. That was found to provide the lowest life cycle costs through the analysis, as Siva mentioned. And it's important to note that why did it cost less? Well, it does have a little bit of a premium in terms of initial cost. However, based on the analysis that we found, we were expecting that plain black bar and epoxy coated rebar would both require major condition-based rehabilitation through the life of the deck within the 75 years, whereas this ASTM steel, the chromium content steel, was able to have that longer life, and we anticipate will avoid that rehabilitation. So now let's talk about a couple monumental bridge examples where we are willing to make a little bit more effort into the design analysis so that it can be more customized for that bridge. We had a design bid build project on our Interstate 895 in Maryland. It was replacing a 60-year-old structurally deficient bridge, 3,300 feet long, and an attaching Holabird Avenue ramp that was almost 600 feet. $189 million project, roughly 2 years. This project was anticipated to induce, and actually did induce, roughly 18-minute delays every day from the reduced lanes that we had during construction. And that's not just like the normal delay, that's how much delay we added to people's lives from this construction project. Because of the magnitude of the traffic impacts and the different costs for the options, it took us 12 years to get the political support to actually have a design that could be supported to move forward. We ended up actually doing a second project to add lanes on I-95 that helped to supplement to get us down to that 18 minutes. So it was an enormous effort just to get this project embraced from the start. It also was astronomically difficult in terms of crossing 23 railroad tracks owned by 4 separate railroad companies, 3 Baltimore City streets, 3 interstate ramps, and went underneath of I-95 and into the Baltimore Harbor Tunnel. So we were constrained vertically, horizontally, I mean, you name it, this bridge was just a nightmare. So one thing that we knew, we did not want to come back here. Once we replace it, we wanted to get in and get out and not interfere with people's lives again. We were not adding capacity because we weren't able to widen given the footprint of the railroad tracks and the amount of property that we owned wasn't really appropriate. So we did set a 100-year service life goal for this project and really wanted to ensure that using an avoidance strategy. I talked about those different approaches earlier. So we did, you can see in the one picture up in the upper right-hand corner, we utilized jointless bridge designs and minimized the number of joints. The picture on the screen is at a bridge abutment where we relied on a deck extension to where the joint is behind that little extra back wall in the front and drains out. This is actually a VDOT standard detail for joints that we incorporated in Maryland for this project in order to separate the bearing line. One of the things that we were able to do with the project is leverage we ended up using solid stainless steel, and we did, however, have a customized deck design. And so based on the cost of the job, we estimate that it was over $3 a pound for that stainless steel, which added roughly 1.4% to the cost of the overall project. However, we never had the pricing of epoxy-coated rebar and using a standard design to compare the additional pounds of steel for that design versus this design. So we do know that we had some cost savings from that customized deck that's not considered here, but the emphasis of what we're trying to show is that there are additional costs with solid stainless. Another monumental bridge project that we have ongoing right now is a design build project in southern Maryland. It's replacing an 82-year-old 1.9 mile bridge over the Potomac River. It's being replaced. I talked about the different reasons that drive service life. This one is being replaced due to the functional service life being sort of eroded and the life cycle costs. We are approaching the need to do a major deck rehabilitation on the existing bridge. The costs and the traffic impacts on an already difficult location drove us towards that replacement option. In this project being design build, we did allow both for performance-based contract and allow for alternative technical concepts where the contractor could present their own ideas for how to achieve our overall goals. The MDTA board, because of the magnitude of this project, did weigh in specifically on what our goals should be, including the service life that we should have for the bridge. And they requested that we achieve 75 years with the expectation that the service life would likely be driven by functional requirements and not durability needs. And so even though we had that durability goal in the contract of 75 years, our contractor, Skanska Corman McLean, in their proposal offered a 100-year design as part of their best value solution, and they were ultimately selected. The performance-based contract had a number of tiers of provisions in it, and we had some avoidance requirements, like having jointless details, and you can see on the screen the pier cap there has that same kind of deck extension that keeps all of any drainage away from the bearing line. And we also required some project-specific performance requirements, like being able to jack the bearings to be able to do bearing replacements and the like. And I'm going to turn it over to Siva to talk about how we actually achieve these with the contractor.
So whenever you're designing a new structure, one of the goals of yours is to be able to say, you know what, we initially in the design phase, we can incorporate materials and systems in such a way that this will achieve a service life of 100 years, which is equal to same as the design life. So Will was talking about some of the deemed to satisfy, where you have those drainage details, you have joint details and things like that. But we also are looking at what's going to happen to different parts of the deck. As you can see, different parts of the structure. You got a lot of different variables here. Deck barriers and piles and piers are all 100-year service life, and the tubs that hold the footers, they're about 75-year service life. Bearings, expansion joint, they all have different service life requirements. And so when you're developing, one of the goals of this project is, or the requirement for this project, is to have a corrosion protection plan developed in the design phase so that the owners can look at how the contractors are going to achieve this required service life and have proposed a plan to achieve that. Our goal is to work with those contractors to develop those plans and be accepted by the owner before they proceed with the actual construction. And so that's what we did, identified all these replaceable, non-replaceable, the requirements for each of those replaceable, non-replaceable elements, and trying to figure out how we're going to achieve the service life. And I'm going to share with you some of those things. As you can see here, your deck and parapets are exposed to de-icing, and one side of the parapet directly exposed, the other one is not. Any overhead sign structure is going to be exposed spray-wise, and then underneath the deck, the superstructure and the substructure that's above water is not going to be exposed except to the atmosphere. When you get down close to the water, now you're talking about splash zone, you're talking about submerged, buried. So lot of different variables. Even in a simple structure like this, you have even different elements having different exposures and need to be addressed in different ways. Having a plan ahead of time to clearly communicate whether it's a pre-stressed piles, whether it's a regular concrete footer exposed to splash zone, whether it's a concrete deck, regular concrete deck, or it's a post-tension box cutter, whatever you have in the plan, you will have to reflect those. You'll have to address how you're going to get 100-year service life. And that's kind of where we ended up going in doing the analysis. One of the things we did is, in the process, is the key things that we have to achieve 100-year service life, which is, we know for sure the piles that's exposed to almost 3 different environments, the same pile. So which one is the controlling one, right? We have to identify which one has the least service life, and that's the controlling one. Which splash zone is going to be the most severe corrosion, right? So looking at that, if that satisfies, then the pile itself would be fine. And we had to look at the soil, look at the corrosivity of the soil as well, to make sure that's not controlling. So when you look at these things, you really want to analyze each element through the service life modeling, predictive modeling, to figure out what particular condition that's controlling, and use that and propose how much cover you have to have, what kind of concrete you have to have, and what happens if you have a cracking, and we'll talk about that as we move along. So some of the other things that we have to address also is, what if you have ASR issue? What if you have freeze-thaw issue? How do you address that early on in the process so that we don't have those issues when the structure is actually built? So we identified a number of tests that the contractor has to do on a given approved mix that will pass some of those details before they can use that mix into the structure. And looking at this, as you can see here, we had identified all those different elements, piles, footers, deck, barriers, and we also identified what is the maximum allowable chloride migration coefficient that the analysis would allow us. And then we actually collected the samples of those particular mixes that the contractor was going to use and actually tested that in our lab and find out what the chloride migration is going to be, which is right at the last line here. That migration that we got should be less than the maximum allowed. We made sure every time they had put a mix together, we made sure that the mix has a chloride migration coefficient that's acceptable so that you will have the performance that you're looking for over 75, 100-year service life. We've done that. And I think that's a good way to actually not only design something to make sure you're also getting it in the field. And so it's a full circular process. You analyze, you get your numbers, you get that as a maximum, and then you actually test to make sure what's going in the structure is going to have that or a better service life. And then what happens when you go into the structure, sometimes this tub that we're talking about, right, it's a 75-year service life. They use the, stainless steel for that, so they don't have to worry about it. Of course, they're pouring concrete into this, the regular concrete, regular steel. And so what happens when the tub is fitted into the pile, it wasn't a perfect fit, concrete to concrete. You all expect that. Most of the time it's okay, sometimes not. And so water started coming in. How is that going to affect the service life? Water is, brackish water. How long it stayed. When we did the analysis, we were able to say, yeah, that's not going to affect your service life. But these kinds of things happen in the structure in real world. A cracking occurs on a pile. Is that going to affect your service life? What do you have to do to bring that service life back to where you need it? And so I'm going to turn it over to Will to close it out.
So in conclusion, as I mentioned a couple times, today's code provides for a 75-year design life, but does not lead to designs that may align specifically with your goals. At MDTA, we had the goal of trying to minimize life cycle costs, and we needed to do the analysis to prove that. And so there is some effort that goes into that, but it really, in terms, what we're advocating here is that you actually know what you're getting. A lot of owners will make the investment and focus on having good detailing and having good standard details, which often are an avoidance strategy, but may not necessarily mean that you get the outcome that you think that you're getting when you start to look at what are you getting from your actual suppliers, what are the actual clear covers you're getting, what does your design lead to in terms of service life. We do recommend that you evaluate your service life position, and that includes in terms of those larger performance-based contracts where it's expected that you create some flexibility for innovation with a contractor on larger jobs to try to save money. But it's important that you say what you want. Even though we are doing performance-based contracts, if you know as an owner that you want something, don't leave a contractor guessing on that. Specify exactly the areas where you do want to avoid or you do have deemed to satisfy criteria that they must meet. And then that actually creates more of a level bidding field in projects. And in conclusion, one of the things that we tried to show with both standard designs and our performance-based contracts is that good engineering and practical designing is still better than just being decisive, right? As owners, a lot of times we like to make quick and good decisions and feel solid about it, and that's great. But at the same time, there are certain instances where you just need to do the analysis and know what your decision actually means. I look at the example on the bridge as a special case. We actually used a galvanized grid deck on one of our bridges over a river, and the reason for that was we needed to upgrade our barriers to MASH compliant barriers through the rehabilitation process. It couldn't handle the extra loading, so there again we migrated away from a standard design. So with that, I am happy, if time permits, Rod, I'm happy to take any questions. Siva and I. Yeah, that we have standard specifications that provide a standard mix design, but the specific contents of the mix deviate just enough within the thresholds that it had a significant impact on the analysis and what service life we were projecting. I'll let Siva comment on that further if you.
Yeah. Well, one of the thing is, in a concrete mix design, you may say you want this much cement, this much aggregate, this much sand, and this much water, and any admixture that you have. You could say that. But we never say anything about temperature, how much you have to mix, how long you mix, when did you put it, what kind of water they added before they put it down, what kind of water they used to finish. A lot of things go into that. And so when you're looking at it, you can design a mix, but what really happens in the field, what goes in the field could be a little bit different. They're generally within the range, and that's why we got the Mix 6, which has got those limits. They use those, and even, for example, the cement from a different source can behave differently. You got to keep that in mind. A cement with a certain chemical in it will react differently than others. So there's a lot to it in a mix, and so there will be variation. This variation for a black steel is not much. I've seen variation that could be 2 years to 25 years, right? I've seen that too. I've seen, a lot of different ways it goes. And so it's typical variation occurs. But that's why you have to make sure you know what the variation is. You design the variation into your analysis.
So you use supplier number 2 all the time?
Not necessary. Not necessary. You may actually, you don't have a control over which supplier the contractor is going to use. I'll tell you this, on a new project that we designed, we had insisted on the designer contractor to have a backup source. And they said, why do we have to do that? We already have a contract, he's going to supply. I said, what if he stops supplying tomorrow? He'd never do that. And they said, okay, we'll go ahead and do it. And I'm glad they did it, because right in the middle of the project, one of the source wasn't available. They came back to me and said, oh, we're going to do it. Well, you got another one, move on. And the project proceeded. And the project is at really good pace. I'm pretty much impressed with that project pace. And that's because we had done the work already. So source may not be there. I can tell you, stainless steel suddenly vanished, right? If you had specified stainless steel, no other option, it vanishes. What do you do?
I did fail to mention too, as Siva mentioned, we did make in our standard design that switch to the A1035. However, we try to avoid sole sourcing any product, frankly, and so we do allow stainless steel as an alternative. But frankly, to date, no contractor has actually made that change, but it is available as an option if the pricing were ever competitive. There was another question, I think, in the back, if there's still time, right? Yeah.
There you go. We got another presentation.
I'll say from the Maryland experience, that's one of the reasons why we provide the stainless alternative, is to not have that excuse, right? We talked about supply chain. But to date, we have not had any trouble with that. We have been able to get the supply for all of our projects, and I think we might hear this in the next presentation about how great of a client we are to work for because of how much we're using it. But no, we haven't had any trouble getting it to date. Now, if every owner in the room switched, I don't know. Yes, sir.
Well, no, we did say the galvanizing is 45 years in our analysis. But when you talk about painting, the painted material required only a 33-year service life. Is that what you're referring to?
Where, I'm not
I
sure
don't know where you're
where you
looking
saw that. Is this the slide you're referring to? Oh,
That is service level requirement.
this table is not intended to imply what we are saying galvanizing or metallizing could achieve. This table is the minimum service life criteria that the design builder had to provide for those elements. So if they could have done a two-coat system that would have gotten 33 years, we would have accepted that. Galvanizing, we certainly would have accepted as that duration, the 33 years. That wasn't meant to say this is what the service life we expect. This is for these bridge components what the design builder had to demonstrate they would achieve, and they were allowed to exceed that. Yes, sir. That's correct. You're welcome. Thank you. Oh. Absolutely. I mean, so that project that we had on the screen here over the Potomac River crosses between Maryland and Virginia, and the bridge abutment is entirely located in Virginia. So we had to have a agreement with VDOT on the limits of ownership specific to the structure. But Maryland could not own property in Virginia. So even though the bridge that's 1.9 miles, we own all the way to the shoreline in Virginia. So we collect all of the toll revenue from this structure. It's basically our bridge. We are funding all of the project except VDOT contributed $13 million in order to be able to secure the parkland and the right-of-way in Virginia, which was enormously complex negotiations between the two states to get that worked out. But yes, we did have to secure the right-of-way. All right.
Well,
thank you.
Thank you, Siva. Thank you. Thanks, Will.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.